Hello everybody, how's it going today? My name is Connor. Welcome back to another video. In this one, I'm going to be talking about how I got my uh, digital logic simulator, the padls, to uh, have GPU acceleration. So, first things first, I've been away from my code for a bit, and it's been kind of chill to just kind of, take a step away and just kind of focus on myself and all of that. So, oops. So I've just been kind of relaxing. I haven't worked on my code very much. I got kind of worked out a few months ago, 2 weeks ago. I don't know how long it's been, but couple months ago, I got pretty burnt out and kind of been focusing on relaxing, not trying to think about code too much, and that's been really good for me. And I'm kind of getting to the point now where I'm getting burnt out of the things that I was doing instead of code. So naturally, I just kind of tend to switch over back into code mode. So this is just like a warm up that I had in mind for kind of getting myself back thinking about code again. Um, so yeah, I had this idea to add GPU acceleration to pedals, um, and that's basically what I've done over the past couple of days. Um, I The reason for wanting to add GPU acceleration into this is because Paddles itself is, just to recap, it's a digital logic simulator, so I can run it and see what it looks like and all that. I can add in, I got the inputs on the left, the outputs on the right. Also, there's a brand new interface to this as well, new GUI that I've added. Which is pretty fancy. It's powered by eGUI, which is a really nice great for media mode, GUI action, graphical user interface action. So you make it in dark light mode even. It's sorry for flashbang, but it's got cool features of the GUI. Anyway, point is, this is running on the GPU now. The simulation itself is running on GPU. This code. Um, the reason why I want to do that is because the way Battles is kind of structured is that it has these, it simulates logic gates, right? A flow of current, a flow of electricity through logic gates, a flow of binary information through logic gates to create compound circuits and all kinds of things like adders and memory and all the building blocks of a computer, right? Um, so um, and in this simulator that I've written, every logic gate and every signal is actually an independent asynchronous task, meaning that it doesn't care about what happens outside of the simulation or outside of its own like part of the simulation, right? So, um, like, if you have like, oh, I don't know if I can. Do I have like a paint of some sort? I can draw with. I guess we'll open up GIMP. Oh crap. I want to create a visual for you guys. So, okay, that'll work. Say I have like a gate over here and a like logic gate over here. These are really bad illustration, but you get what I mean, right? They have like a really simple like 4 input 1 output gate or something like that, where it's like um I don't even know what gates these are. It's been so long since I've done this. But like for instance, this gate here only cares about this, and that's actually about it. It only cares about its inputs. It doesn't care what's going on over here. This gate does not care about what's going on over here. It only cares about what it needs in order to produce its output. So I figured that would be a really simple thing to kind of translate into a graphics card shader, because the way that graphics cards naturally are designed is as parallel processing machines. So if I had some kind of way to get the state of all the signals into a graphics card shader, and kind of, per graphics card core that the shader operated on, which would be, it would be one per each one of these gates. So in this case, it'd be like 3 cores, all operating on the same circuit, but they're all part of the same circuit, but they're operating independently of each other. And so if I could like just modify this state of this circuit as like a big vector or a matrix of some sort, then I could just, reuse that over and over again, and just have the little individual instances of the work group for the graphics card shader, for the compute paths or whatever. I don't know. I'm still very new to all of this, but I'm just going to share what I've learned so far, just because I think it's really interesting. So, I'm excited about what I've done so far with it. So, anyway, let's dig into the code a little bit. This is actually, so I'm using WGPU, which is a Rust crate for the web GPU standard. WGPU core set of implementations of how to get your graphics card hardware to talk to Rust applications. Basically, it's a Rust crate for using GPU stuff. That's all I really care about. I could use the CUDA bindings, but that involves lots of unsafe, and I just didn't want to have to do a whole bunch of unsafe. So WGPU uses things like Vulkan and OpenGL and DirectX under the hood. It's just a wrapper around all those with a common API, which I figured would be really cool for my application since it's a cross-platform anyway. So I didn't want to tie down my application to one individual graphics backend, so I used WGPU. Plus, I just wanted to learn how WGPU works because I think it's a cool concept. So, either way, yeah. So here's a shader I have for the circuit, and we'll get into like how I glued this all into the actual application in a bit. But it's kind of just the core of like what's happening here. And let's see. So what I have, these are basically these bindings, or what I'm passing into the shader from CPU land. So I have a array of inside 32-bit integers that are states, and really I really wanted these to be like booleans or whatever, because they're really just 1 bit each of data. They're 1 or a 0. There's nothing else. But WGSL, the graphics shader language for WGPU, web GPU, is doesn't let me do booleans as a binding. So I guess that makes sense, because GPUs typically operate on a minimum of 32-bit values, like float 32s or whatever. So anyway, so I'm passing in a bunch of 32-bit integers. I've got this is kind of like my poor man's mapping, poor man's map, or like dictionary if you're a Pythoner, where it's an array of pairs of 32-bit integers, and these are the indices into this array, into the states of what the inputs are for each of the gates in order, right? So say you have like if we go back to this example, say like this is like 1, this is 2, this is 3, right? So the entry at the index of the states that 3 is at, so like say we have like 1, 2, 3. Sorry, this would be like 0. Let's do like 0, 1, 0, right? This is that 0, 1, to index. So say this is like the index, sorry, this is a state of what these bits are. So like this would correspond to that, right? That would correspond to that, correspond to that. Actually, let's actually make this like sorry, this is like really scuffed, but this actually be oh, now this is too big. 0, 1, 2. Okay. So like this is currently a 0, this is currently a 1, this is currently a 2, right? So sorry, this is currently a 0 as well. God, this is so confusing. How do I even do this? So like this is at index 0, this is index 1, this is index 2, this is currently containing a 0, it's currently containing a 1, this is currently containing a 0 as well, because hopefully you get what I mean by that. If you have questions, leave them in the comments and I'll try to explain it even better. So anyway, so the inputs array contains like at index no, I'm not going to try to explain it. It's just it's a mapping of like what the inputs to each of these gates are. So you need to know that this is the array that contains that information. And the modes is just what type of gate each index of the states is. So what do I need to do with that? So the states is like the outputs of every gate. The inputs is containing which ones do I need to look at in order to determine the output at my location. And the modes is what operation am I doing at for my output at this location. So anyway, and then all we really do is we take our global invocation index, which is basically just an identifier for which CUDA core are we working on inside the GPU. It's arranged into like a grid, an XYZ grid. So I take the X coordinate and I use that to index into the states. And you can see here that hopefully if you know anything about WGSO, you can follow along with this, but it's really similar to Rust or like C or what have you, you know, very similar syntax. So you have it will, yeah, sorry, I'm having a brain fart. I've been working on this all day. So it will, yeah, call this eval function that I've created based on what its inputs are, based on the inputs to the gate, the particular gate that we are representing. And this is just the logic, the logic simulation, you know, if we're mode like an identity gate, then we just return the first input, or if we are a not gate, we invert the input, etc. You know, so this is like the WGSO equivalent of like over in gates. We have the actual logic here that's actually happening on the bits. So same idea. Just per bit, per gate, we're operating on the bits and outputting the correct bit, and operating the correct high or low value. Am I doing on time? Sorry, gonna be a mirror for a sec. Okay. So anyway, that's enough rambling about the shader itself. How do I get this running inside the simulation itself? So I've created this kind of helper struct containing the adapter, the device, and the command queue for the GPU. That I can just initialize all this in one fell swoop. It has to be done asynchronously. And so inside some kind of asynchronous context, right? And for this one, I'm using Tokyo because that's one I was already using for the simulation on the CPU side. Um, so, um, and then really kind of the meat of what happens here is in the spawn GPU function. It kind of takes a similar signature to the spawn CPU function. That's not it. Yeah, spawn CPU function here where it takes as inputs a bunch of watch receivers, actually a map of watch receivers to which gate it is, and what its inputs are. And then we return a mapping of the output gates, all the output nodes, and a receiver for looking at what their shit is. So, what their outputs are? Sorry. So a lot of the same stuff is happening in the beginning here. I really should consolidate this into its own method, but whatever. So I kind of flesh out the connections to from the inputs to the actual next gates after the inputs. And then I hook everything up. And what I'm doing here is so we have to somehow get the state of all of the gates, or at least the output gates, out of the GPU eventually, or else we won't be able to see them in the graphical interface, right? So creating a bunch of watch channels. Watch channels are very useful. I can't tell you how useful these things are for this particular project because they're very fast and they're very simple. And so when you have like hundreds or thousands of channels and asynchronous tasks going at once, you know, simplicity is your friend. So, anywho, so I'm populating these maps of transmitters and receivers for getting the output information out of the GPU. So we need to implement the clock. That's something that's probably next on my to-do list. Is I need to get the some kind of clock going that probably runs on the CPU, but its state is updated into the GPU state array that I mentioned before. So okay, so here's where the actual GPU stuff starts. We load a shader, we create a compute pipeline because this is a compute shader. What that means is, it's as opposed to being like a graphics, vertex or fragment shader, this is a compute shader. We're not actually going to be showing anything with this. This is just doing some math for us, basically. How much constants are useful. These are analogous to the ones inside the shader, which I don't actually end up using in here, but it's a good reference to keep track of everything. So this variable here, state length, is going to be how many actual cores we're spawning, how many how many cores we're dispatching our work group into. We just populate all these, and then for every binary gate, so this is, and I use the term binary and unary gate. What they really mean is like, oh, that's not that. These are binary gates, and then these connections are like unary gates. So it can either be a NOT or just a pass-through identity operation. Like this would be like a NOT, right? Inverting the input as its output. This is just a symbol for it in logic diagram lingo, I guess. So anyway, when I say unary gate, it's really just a connection between the gates. When I say a binary gate, it's an actual like AND or XOR operation. You know what I mean? So, so for every binary gate, we iterate over those. We assign it an index into this state array. And then we populate the modes vector as well, the modes array, with whatever the appropriate mode flag is. Still have to implement some of them, but you know, it works for now. Um, we For every unary gate, every connection between the gates, we populate those because now we know what all the binaries are called. um, so yeah. So now we know what everything should be called and what its modes are. Sorry, I had to think about that for a sec. Um, we can now hook everything up in the inputs um, array. That's this one. When I went on rambling about, that turned out too complicated to explain. uh, Populate that with whatever index into the states array that we should be looking at for each individual gate. Then we create our GPU buffers with all this information that we've now calculated. And we create a staging buffer so that we can basically this will notify us when the state is readable. The state vector, you know, that we're already operating on all mutably and stuff. When that becomes readable, when we're eventually able to, you know, when we request a read from it, I should say, and when it becomes available, we what was I gonna say? We basically God, I had another brain fart. Sorry. I'm going through this really fast because I don't have a lot of time. I want to go to bed. But okay, so yeah, this will I'll get to it in a sec. So wait, we spawned a Tokyo asynchronous task. Maybe it should be on its own thread, but whatever. We create our binding group. This binding group is required in order to actually get these buffers into the shader code. Shader execution. So we bind them into the shader. We create a command encoder where we our compute pass. We set our pipeline up, which is just the one that we've set up, you know, with the shader. Tell it what shader we're using. We tell it what bind group we're using, all the inputs stuff, and then we dispatch our work groups with as many compute cores as we have gates in the simulation. Okay. We then copy that buffer into the staging buffer, the state buffer into the staging buffer as the last step of our compute pass. We submit that to the queue, command queue. We need to now map the staging buffer into CPU memory, and we need to be notified when that's ready. So this is just a simple one-shot channel that is used to send us our state. Or send us our notification of when we're ready. So you can see buffer is ready to map once the callback is called. And then we pull our GPU, and now we basically just copy this data out of the yeah. So we copy the state back into itself. Now that we're the state that's in CPU memory, the staging buffer, we now need to update our outputs. Remember, before these are what we're actually returning from this function is listeners for the output nodes of the actual circuit itself. In the main function here, or the main circuit, it's these ones. So we need to tell our GUI that those have changed if they've changed. So we update the state of those by setting them over the transmitter that we created before. And then if any of our inputs have changed, if we need take our inputs that were inputted into this function, pass it into this function, the spawn function, And then we get the latest state of those, and we update the state with the state vector with that state of the bit. And then this just writes the actual thing we've been modifying back into the state buffer that's on the GPU. And that's it, really. And all I did with the actual app code was I replaced one function call with the where was it? On GPU. Yeah. So I'm spawning it instead of a spawn CPU, I spawn GPU after creating the GPU instance, the GPU context that I've talked about, contains all the stuff we need. I pass that in, and it's literally just plug and play. And we're now running on GPU. So hopefully that wasn't too scatterbrained for you guys. I hope you enjoyed this video. I'm planning on uploading more coding videos soon, depending on what I end up working on or when I work on it. Not gonna make any promises or guarantees right now, unfortunately. But what I've been doing mostly while I've been not coding is I've been gaming, because I don't have a job. I'm disabled. I've just kind of been taking a break from anything coding related and just kind of working on my gaming, which I might start a YouTube channel for that. I know probably lots of people who watch my videos are also gamers. So if you guys are interested in anything like MMORPG related or FPS game related or whatever, those tend to be the games that I tend to like. Go ahead and I'm going to leave my gaming channel that I've created down in the description or in the comment or something, and you can find it there, and you can drop me a follow if you want. Again, no guarantees on when I'm going to be uploading content for that, or when I'm going to be uploading content for this channel again, or whatever. I just kind of wanted to put something out there just because it's been a while. So anyway, thank you all very much for watching. I will catch you in the next one, whenever it ends up being. If you like this video, hit a like. If you want to comment on this video, leave a comment. And I will see you on the next one. Thank you very much. Peace out.